factoring the difference of two squares. So what the factoring we've done the last 2 days, they've always been in the form of ax squared plus bx plus c. Okay? Well, sometimes we get things that are in the form of the difference of two squares. So there's only two terms, and they're separated by a minus sign. Okay? Two terms separated by a minus sign for the difference of two squares. And so it's important that A, you know your squares. So 1 squared, 2 squared, 3 squared, 4 squared, and so on. Okay? And then B, this is really easy to factor once you see those two squares. If you see them, then it's as simple as doing the first thing squared plus the second thing squared, and the first thing that's squared minus the second thing that's squared. So the difference of two squares is really one of the easier things we do. All right, so here's an example, x squared minus 9. Okay, x is squared first, and then to get 9, we square 3. So then it would be x plus 3 and x minus 3. So we're getting away from the ax squared plus bx plus c, kind of. All right. The difference is that in these cases with a difference of two squares, the value of b is always 0. Okay. If it's a difference of two squares, since you only have two terms, b is always going to be 0. So the thing we need to know is just, okay, so I look at it, all right, I have two terms, they're separated by a minus sign. So my first thing that goes off in my head after I check for the greatest common factor is, are those two things squares? Okay. So n squared, yep, it is. So in this case, we have n that is squared. My minus sign, right? What squared makes 25? Okay, so this is 5 is squared here. So then I'm going to have n plus 5 and n minus 5. So, and n to the fourth minus 100. Okay. Whenever power is even, right, then it's always a square. Okay. If the power is even, it's always a square. And the thing that's squared is just half of that power. So in this case, since it's n to the fourth, the thing that's squared here is going to be n squared is actually what's squared. So the thing that's squared, you just have to cut that power in half to find it. Because if you remember rules of exponents, we would multiply these two together to get the fourth power. And then we have 10 squared here. So we do n squared plus 10 and n squared minus 10. Difference of two squares. Now the other on your packet from factoring, there will be some other ones that are in that packet with it, or on the ones you're going to do on pages 5 and 6. The other ones on there are called perfect square trinomials. Now I'm not going to go into the whole thing about them, because all it means is if it's a perfect square trinomial, that when I factor it, so I'll give you an example. All it means is that when I factor it, I'm going to get the same thing. Okay? So what are the factors of 25 that add up to 10? Okay, 5 and 5. So this just means we're going to have a plus 5 twice. All right, so I can write it as a plus 5 squared. And we will talk more about perfect square trinomials when we get to that lesson that we're going to do what's called completing the square in chapter 9. But for right now, you're going to do some factoring with these. There's a couple of them on that pages 5 and 6 on the packet, but you can just do them. Either they're going to be set up like this where, yep, that's not a big deal, or there'll be a situation where you say, okay, so a is a number greater than 1, and so then you just use the airplane method to factor it. Okay? So there's no special way of factoring. It's just you can see specific things. We'll talk more about those when we get there in chapter 9. Okay? All right, but that's pretty easy factoring those things. So, all right, chapter 9, lesson 1. This is all about quadratics. Chapter 9 is, and in chapter 8 we did quadratics. Most of the stuff we did in chapter 8 was we multiplied and we factored. In chapter 9 we're going to look at all the rest of the really cool things about quadratics and parabolas, which is actually what the graph of a quadratic is. So a quadratic function is always written in this form here. Right? Y equals ax squared plus bx plus c. Something we've already talked about. Now, b and c, the parent function, what's called the parent function, is just y equals x squared. All right? That's the most simplest version of a quadratic. Okay, y equals 1x squared plus 0x plus 0. And so for today and tomorrow and Friday, we're just basically going to be looking at the characteristics of the graphs and the specific things about them that we can find. Right? So first of all, we want to be able to identify quadratics. Right? Is an equation, is it a quadratic? Or if I have a set of numbers or a set of points, does it produce a quadratic also? And when we were doing linear models earlier in Algebra 1, we found that first differences, if all the x values changed by a constant, and all the y values changed by a constant, we found out that those were linear. And then if we did that, what would be the first differences would be if we subtract each pair of these, okay, then we would get a constant number. But with a quadratic, if we subtract those numbers, then we're checking to see if we have a quadratic then. So first difference tells me there's a linear function. Second differences tell me it's a quadratic. If we went further, third differences would be what would be a cubic function, and we could go on and on with that. But for quadratics, we're going to look at second differences. So we're looking for two things. Right? When we have an equation, right, can it be written in the form y equals ax squared plus bx plus c? If it's a set of points, can those set of points, when I find the first and second differences, are the second differences the same? Okay. So we're going to look at the set of points first of all. So here we've got these points, -2, -9, -1, -2, 0, -1, 1, 0, and 2, 7. And so we want to find out if these represent a quadratic. Now the first thing we could do is we could graph them, right, and see if they do produce something that goes down and comes back up. But as I was telling you earlier, sometimes you can't quite tell because it might just show you half of the graph instead of the whole thing, right? Or maybe they come down in a straight line and go back up like an absolute value function. So by doing first and second differences, we can tell for sure whether it's a quadratic or not. So the first thing we have to look at is, do the x values, or the domain, is the domain linear? Right? So do the x values change by a constant? Right? Because if they don't, then it doesn't matter about the first and second differences for the y values. Right? So we can see here that I've set these up in a table, that going from -2 to -1 to 0 to 1 to 2, that those all increase by 1. So it's a constant rate of change. So we're going to look at the y values then. Right? So we're going to find the first difference and then the second difference. Like, and just a reminder that if the first differences are the same, then it's linear, and so it's definitely not quadratic. And if the second differences are the same, then it is a quadratic. Right? So how far is it from -9 to -2? We go up 7, right? Okay. So this is a positive 7. Right? From -2 to -1 is a positive 1. -1 to 0 is positive 1. And up 7. So the other way to think about this, that's one way to think about it. The other thing is you can think of them as start at the end and subtract. Okay? 7 minus 0 is 7. 0 minus -1 is 1. -1 minus -2 is 1. And -2 minus -9 is 7. Remember, so we're subtracting a negative, so we're adding. Okay? So we do it with these numbers here. Okay? So I'm going to go backwards here. So 7 minus 1 is 6. All right, so we have a positive 6 there. 1 minus 1 is 0. All right, and 1 minus 7 is -6. Well, those are not the same, are they? Okay, so this is not a quadratic. So when you have a table of values, then you're just going to check the first and second differences to see if they're the same. See if the second differences are the same to determine whether it's quadratic or not. So here's an example of one that is not. All right. Okay. All right, so here in B and C, we're going to look at a couple of equations. And so when it's an equation, we're looking for y equals ax squared plus bx plus c. All right. Most important thing is I'm looking for a power of 2. Right. And what's the power for x here? If I just have bx, what's the power for the x? Okay, it's 1. Right? And the power for x in c is 0. Okay? So the biggest power I can have, or exponent I can have, would be a 2. Right? But I have to have at least that. So is y equals 7x plus 3, is that a quadratic? Okay. All right? So here there's no x squared term, so it's not a quadratic function. There's c, y minus 10x squared equals 9. So let's do this. Let's get the y by itself first of all, right, to verify to us it is. Right? I can see it is. Right? But let's make sure let's get it y by itself. So what do I have to do to get rid of this negative 10x squared? Right? So since it's a minus 10x squared, we're going to add it to both sides. So we get y equals 10x squared plus 9. So is this in the form ax squared plus bx plus c? Okay. And it is. Right? Highest degree I have is 2, so this is a quadratic function. Let me give you another one. There, D. So Katie, does this represent a quadratic function?
No.
Why not?
Because there's a power of 3.
Okay, there's a power of 3. All right. Now I made it a trick question. Okay. All right. There is a power of 3, but I'm testing you to see. All right. If you understand with that power of 3 though, what's the coefficient of that power of 3? 0. Okay. So what does this mean then? There's actually 0 x cubes, right? So if I could rewrite that without it, y equals x squared minus 3x plus 5. So because it is 0x cubed, then this is a quadratic function. That was just the test case. Right? Now when you see that, you'll know. Right? So there's identifying quadratic functions. Biggest thing is, can you tell, all right, if I have a set of points, are the second differences the same? If I have an equation, right, is the greatest power 2? All right, let's do some graphing of them. So take out that sheet of graph paper you've got. And the first thing we're going to do is we're going to look at the graph of y equals x squared. So on your paper then, I want you to make sure that, so the scale you make here, go up as far as 9. Okay, so go by 1s horizontally, okay, and then make sure you can get up to 9 vertically. Okay, all right, so we're going to go -1 through 4. And here, I'll just show you this. So it should look about like this. Here's the one you make. All right, so you only need to go left and right 4 is far enough. Go from to negative 4 on the x-axis to positive 4, and then on the y-axis you go from negative 1 to 9. So negative 4 to 4 on the x-axis and negative 1 to 9 on your y-axis. Right? And we're going to make a table. And let's see. All right. And make a table. So it's from negative 3 to 3 on the x, and then we'll do our y. So with quadratics, all right, especially if it's just in the form like y equals x squared, if there's no bx and no c, then it's always just going to come down and go back up, or go up and come back down. All right, so we're going down from 9 to 0, then back up to 9. All right, so let's plot these. All right. I always like to, when I plot them, I always like to start with the origin. All right, 0, 0. Now, most of quadratics, when it's just x squared, we're going to go over 1 each way and then up 1. Okay? So negative 1, 1, positive 1, 1. And then we go left and right 2 and up 4, because 2 squared is 4. Okay? And then over 3 and up 9. And we have y equals x squared then. Right? This is your parent function. Right? Every graph from every graph that you make that's a quadratic is going to be this graph right here. Let's see if I can get it to work for me. This graph right here. Right? There we go. But transformed. Okay? So it might be moved left or right, might move up or down, might go upside down, all right? Might be fatter or skinnier. So, but everything goes from there. So having a good idea of what they look like and why they do is important. The normal one is always at the origin, over 1 up 1, over 2 up 4, over 3 up 9. Okay. All right, so let's look at what happens when we do a little transformation of it then. Okay, so here we're going to graph y equals 1/3 x squared. Let's back up. Actually, I'm going to just have you do it. Okay. So you're taking those numbers, all right? So this is the main part of this that I really want you to understand then, is that all I'm going to do is I'm going to take these numbers here and I'm changing them, all right, a little bit. So since it says it's 1/3 x squared, that means I'm going to take those numbers and I'm going to do what with them? Okay, we're going to cut them in a third. Yep, okay. We're just going to multiply those numbers by 1/3. So the numbers that we had for negative 2, negative 1, 0, 1, and 2, so 4, 1, 0, 1, and 4, those are our main numbers of when we have x squared. It's just now we are going to do 1/3 times those x squared values. So all I have to do is multiply them by 1/3. And you could just leave them as a fraction. I would. Just as easy. Don't worry about decimals with these. Okay? If they give you fractions, work with fractions. If they give you decimals, work with decimals. But one thing you'll find is that I prefer fractions over decimals any day. Right? They're a whole lot easier to work with. So when we graph negative y equals negative 4x squared, we're just going to take the numbers we get when we square these x values and then just multiply them by negative 4. So we get negative 4 times 1 is negative 4. Negative 4 times 0 is 0. Negative 4 times 1 is still negative 4. And negative 4 times 4 is negative 16. So for those, you just focus on, okay, the parent function, y equals x squared. And then what am I doing to that? Okay? Just multiplying that by some constant, those x or those y values then. Right? And then graph them. Now, the thing is that, like we said, most of the time you're going to have a calculator to your disposal, okay, to use. And so you can always then check these things to make sure that they work. And I don't know, my table decided to add some numbers to it. Oops. There we go. Oops, that one's got. There. Okay. Graphing. Okay. Now, we're going to do this for a second. All right. I'm just going to tell you. So take your calculator for a minute then. And we're going to do a little exploring here, all right? And then we'll look at these notes. All right? Do a little exploring, all right? I want you to graph these. Okay, graph those three functions graph all three of them on your calculator. Now, if you have a problem with the fraction, just put in 0.5. Okay. All right. So what do they look like? A hodgepodge. Okay, it looks like a hodgepodge. All right. But if you were to explain in general what those look like, what would you say? What's one thing you would say the characteristics of those three graphs? They all do what? They all open up, right? Okay. They all open up. All right, now I want you to do this. Okay. I want you to, and this is how you do it on the calculator, so let me, I want you to change the first, make the first number negative on all of them, okay? So hold on, don't clear anything. All right, I'm going to tell you how to do this the easy way. All right, so I don't know what they are, so I'm just going to put something in here. Okay. All right, I want you to change the x squared term, the first term, to be negative, okay? So here's what you do. Do second, delete, so insert, and then put a negative sign there. Okay? Second, delete, that's insert, then just put a negative sign there. Okay? Do that on all three of them, and then regraph them. All right, so what's the main difference? Okay, they opened up. All right, so here's the rule. If A is greater than 0, they open upwards. Okay, so what does it mean to be greater than 0? Okay. Positive. Okay, so here's my crazy way of thinking about it. Okay, so when you're feeling positive, what do you do?
Smile.
What?
Smile.
You smile. Okay, all right. And when you're feeling negative, what do? You frown. Okay, so when A is positive, the graph opens up because it's smiling on you, saying, hey, it's a great day. All right, and when A is negative, then you're feeling sad and you frown. Okay? So opens up when A is positive, opens down when A is negative. All right? So you've got a smiley face and a frowning face. It's way more fun to have a smiley face than a frowny face. Right? Okay. So, what do we want? We're looking for A being positive. So we want to make sure that it's in this form. Y equals ax squared plus bx plus c. So that means that we might need to solve for y first of all, move things to the other side of the equal sign to do that. So we want to get y by itself. So what do I have to, so here we have y equals negative 1/4 x squared equals x minus 3. What do I need to do to get y by itself? Emma, what do we do? Okay, good. Yep. All right, we're going to add 1/4 x squared to both sides. So we get y equals 1/4 x squared plus x minus 3. So my concern is the value of a. So Whitney, what's a? What's a? What's the value of a here? What's the value of a? Do you know? No? Okay. Remember, a is the thing, the coefficient of x squared. So what's in front of x squared? What number's in front of x squared? All right, Sabrina. 1/4. Okay. Is 1/4 a positive or a negative number? Okay, it's positive. So this means it's greater than 0. So this graph is going to open up. Letter B, y equals 5x minus 3x squared. Does this graph open up or down? And why? So all we have to do is look for the x squared term. Okay? As long as y is by itself, we just need to look for the x squared term and find a. So we could rewrite it. Case, what's the value of a? What's the number in front of x squared? -3. So a is equal to -3. Is that less than or greater than 0? Okay, it's less than 0, it's negative, so this is going to open downward. So if a is greater than 0, opens up. A is less than 0, it opens down. All right, we're going to stop there then.